Hello, everyone. I hope you're all feeling great and still enjoyed yesterday's sessions. Well, because day two is here, and yet we're just getting started. Our next speaker is someone who truly brings intelligence to innovation. Ilham Bakkar, an AI engineer at Trella Base. She's the
Sure.
kind of mind, okay, thank you. She's the kind of mind that doesn't just imagine the future of AI, she builds it. With a strong focus on AI agents, ML, MLOps, and scalable AI architectures, Ilham turns complex concepts into real working systems that make a difference. Her session, Engineering Multi-Agent Systems, Patterns for Production Success, will take us behind the scenes of how smart systems collaborate, adapt, and perform at scale, the kind of knowledge that turns ideas into impact. So, I hope you all will enjoy this session. You should not miss it, and the stage is yours, our dear speaker.
Thank you, Hala. Hello, everyone. Thank you for the great introduction. Thank you, GDG Algiers. It's a pleasure always to participate with you in your events. So this is Ilham Bakar. Hala already introduced me. So today we are going to explore a topic that's shaping the next generation of AI infrastructure, the engineering of multi-agent systems, not just from a research perspective, but from an engineering and a production standpoint. How actually, uh, how actually are we going to build, deploy, and scale these systems in real-world environments? So, according to a recent MIT research, 95% of generative AI pilot programs fail. So they fail to achieve measurable business impact. And as you know, we are always, as engineers, we are replying to a business problem. So the issue was never about the models themselves, because we are using high quality models. Even if you don't know how to build models, you have APIs. The problem and the main issue is in the architecture. So we are not talking about models. We are not talking about APIs, but we are talking about systems. However, most of the organizations still think of AI kind of a simple model or a collection of isolated tools, just like a chatbot here or a summarizer there, each optimized for a single function. But in fact, we are moving beyond of this. We are moving from models and simple tools to systems. And and here we will find the multi-agent systems comes in. So they enable us to move on from simple task automation or simple task prediction to process transformation. And as engineers, the problematic today is that we are not working just with research demos or simple models. We are expecting to deliver a high quality software components, because as engineers, we are playing with other engineers in a huge ecosystem. So those softwares should have kind of measurable outcomes. So either in efficiency, in reliability, and at the same time a return of investment, as we said, because we are answering a business problem. So the goal today is to look at how we can design and engineer a multi-agent system that actually meet those expectations in production. Let's start from the baseline, the single agent architecture, what most LLM applications today still use. So imagine deploying a single large language model that handles, let's say, a process. So this process contains many steps For example, if let's say a process is about customer interaction, for example. So we have, for example, customer interaction. We have some data retrieval. There is a reasoning behind, and there is an output generation. So everything is done by one and only one agent. It means that you will put the whole scenario in one context window or one prompt, and then imagine that this big prompt is going to have a context, of course, because you are using your agent inside the session, and inside the session we have a context that is going to be incrementally added, and then you will reach kind of a limit where your agent is going to perform bad after even performing well for the first steps. So it might work, but for small and well-defined tasks. But if you go bigger, or you try to make the thing maybe more complicated, then your agent is going to fall down. So a single agent that tries to be, for example, or to do many steps, generally will stop after many many trials. Or if we try to add more complexity, then it's gonna throw some trash at the end. And it's become something we call a monolith of AI. So the word monolith at the beginning was used with software engineering, and today we are using it in AI as well. So once it becomes a monolith of AI, it's going to be difficult to maintain, kind of nearly impossible, and we will not be able to augment it, or to for example add more complexity to the tasks. From an engineering perspective, we say that single agent suffers from mainly four limitations, if we can summarize them. First of all, as we said, the context overload. So if you have many tasks to do, everything is explained in one prompt, and the model is always, of course, receiving more context that is going to be added into your session. So the prompt is going to be very big. I'm talking about the prompt that we are sending to the model, to the LLM. So it's going to be very confusing for the model, and after a while, it's gonna just throw some trash by the end. Sometimes it forgets. Sometimes you will see that it's not following the steps as you mentioned, etc. Second, we have the role confusion. So asking one agent to do everything will create something we call identity crisis. So kind of it's after a while it's gonna do nothing. The third point is that there is no specialization. Um, it can be understood as a role confusion, but what do I want to say by it is that, for example, if we have, let's say, many tasks, or a list of tasks, sequential tasks, each task requires kind of a small prompt, requires to use, let's say, some tools. So by the end, if you put everything together, you don't have kind of specialists inside your chain of agents, or chain of tasks, if you want. So the agents will not be able to optimize across conflicting requirements. And the last point is that is what we call the poor error recovery. It means, imagine you have a mistake at the beginning of the workflow. So this error is going to be propagated through all the next steps, and the worst thing is that you are not be able to isolate the failure, or to localize the error. We will talk later about something we call observability of the system, where we will try to have kind of an overview about the whole system, and to effectively to localize the errors and the failures. In that case, it would be very difficult to localize the failure, except if you build the system by yourself. So you are not using frameworks and you try to put some logs inside to check them. Another thing is that it's not scalable. So if the workflow is going to be more complex, then that's a problem. And the maintenance is going to be a nightmare, to be honest. So specialized tasks need kind of specialized reasoning. That's why we go to the multi-agent systems that tries to overcome those limitations. Now, talking about multi-agent systems, or what is a multi-agent system, it tries to address an issue by decoupling the reasoning and coordination. So instead of having a single overloaded agent, we try to build a team of specialized agents that communicates and collaborates. And those are the most interesting things: communication and collaboration. So, as it was defined by IBM, it's a system that is composed of multiple autonomous agents interacting within an environment to achieve goals that are beyond of individual capabilities. It means that, for example, the big image is not going to be done by one of the agents. So the big puzzle is going to be kind of built by the whole team. And of course, each one of the agents has its own role. So we can see here in the illustration, it's just an illustration of one kind of the architectures of multi-agent system, which is the coordinator architecture, or the supervisor architecture, where we have kind of a team leader. So the query is going to be received by the team leader, and the team leader will plan the steps and send each sub-query to the appropriate agent that will solve it. And then by the end, everything is going to be sent, or all the responses are going to be sent to the coordinator. It's going to summarize everything and send the outputs. Here I'm putting like the whole image of the system. Of course, if we are using a multi-agent, it means we are keeping all the concepts of the agents. We have, of course, a memory, which is a very strong concept in the agentic field. So the the whole system will communicate with the memory. How? It depends on your design choices. Now, for the whole system to actually work, there is kind of three ingredients to have. So first of all, there is an autonomy. I mean, those characteristics, you need to take them into consideration or to understand them, so that when you try to design your own system, you will design it correctly. First of all, the autonomy of the agent itself. It means that, for example, the first agent should be independent from the other agents, so it can take its own decisions based on the local perceptions and goals. What do we mean by local perception? It means what the agent has as tools, as context, as access to memory, because we can have, for example, the whole context of the agents, the system, and we have the local context of the agent. Sometimes we don't let the agent has access to the bigger context. So always the agent should act on his own environment, or should be able to act on his own environments. The second point is specialization. So when we start designing the system, we try to divide the tasks according to speciality, if you want. For example, one agent that does the web search should not do, for example, content generation or some other designs, for example, um, let's say image generation. So I will try to isolate and make kind of specialties for our agents. The first one is going to work on the web. The second one is going to work on designing, for example, pictures. The third one is going to work on the content, the textual content, etc. The third one is interaction or the communication between the agents. This is very interesting, and building a strong infrastructure of communication is a key of the success of your system. If you are building your system from scratch, or if you are using some frameworks that are poor or that are, let's say, low level, I won't say poor. There is some frameworks that works very well. They handle all the infrastructure and the interactions. For example, Agno, I really appreciate it, and I'm using it actually. So they have a very good communication infrastructure. The last point is environments. What do we mean by the environment? As I told you, so we have the tools, we have the access to the context of work, the access to the memory. Mainly those 3 points. So the tools, the context, and the memory. Now, moving to another point, which is when to use the multi-agent systems, because sometimes we have some trends, and when the trend comes, everyone goes after the trend, if you can say this. So once the multi-agent systems comes, everyone wants to create its multi-agent system. So when to use it, it's very interesting. Why? Because they are very, I won't say very, but they are costly. So if your problem needs a multi-agent system, then go for it. And try to choose the right architecture to not make things very complex to you. If it doesn't, then avoid them. So when to use it? First of all, if the problem can be broken into specialized subtasks with clear boundaries, I always put a stress on clear boundaries, because sometimes we try to create, for example, 2 sub-agents and they have kind of similar or let's say similar definition, and then your orchestrator or your supervisor is going to suffer to choose which one to use, and then it's going to be a problem for you later when you go to the testing part. The second point is when you need a domain specialized reasoning. For example, if you have a sequential process and you need to go in depth in one of the steps, then here it would be interesting to have it as an agent. If you need as well to integrate multiple models or tools, especially the tools, because sometimes if you put, for example, one agent and a lot of tools, it would be really difficult for the agent to choose the right tool. And the last point is scalability or parallelization matters. So if you think that your system is going to scale, then consider an architecture of a multi-agent system. What to avoid is that when your task is sequential or simple. Sometimes if your task is sequential and you think that there is some steps that needs kind of in-depth knowledge or in-depth tasks, then you can go for a workflow. A workflow is a sequential architecture of agents. If the overhead, the problems are more than the benefit, then avoid. If the shared context is small or static, then you need to think about it as well. So one quote that I liked from Long-Chain Guidance book is that if the multi-agent systems are used when the value justifies the cost of the extra complexities. It's true that there is a lot of benefits, but you need to kind of have a trade-off between complexity, cost, and coordination compared to the to the real value. Um, Now we move into the core engineering section, which is the architectural patterns. Actually, we have many patterns. I tried to organize them into four or five patterns. So we have the single agent, the simple one. We have the network multi-agent. We have the hierarchical multi-agent. We have the workflow and the supervisor architectural pattern. We start with the simple one, which is the single agent, just to refresh your memories about what does it mean, an agent. So here it's only one, and the simplest one to understand. In this approach, we only have one LLM with a host of tools. Where is my mouse? So we have a model, which is an LLM. We have a host of tools. So this model is going to answer a query based on some prompt, and it's going to use the tools to answer it. Of course, there is an access to the memory. A memory, we have two types. We can say three, but actually, we will discuss them later in the presentation. We have a short-term and a long-term memory. And of course, the model has a list of steps, steps of reasoning or planning to answer that query and send a response. Moving to what do we call supervisor agent architecture. It's the same as the one that we had in the previous example. So we have a single supervisor agent that will act like a central control. So the query is going to be received by this supervisor, and then it will decompose the tasks and delegate them to the specialized agents. And the sub-agents will handle the subtask and reports the answer to the supervisor. This supervisor or the lead will integrate the results and ensure alignment with the global goal. So ensure that we are answering the global or the inputs. Now, talking about the pros and the cons of this architecture. So, first of all, about the pros, it's simple to debug because we have kind of a linear flow, and it's easy to trace. It's the predictable execution. So it's kind of a deterministic behavior. If it's kind of an if and else, you see. If the topic is one of the specialties of the first agent, then it's going to be sent here. If it's a specialty of the second agent, it will be sent there, etc. And it's easy to enforce with system-wide rules. If we talk about the cons, so it's if the main problem is that if the manager will shut down, so your entire system will stop. So one failure in the supervisor will stop the whole system. The second point is that the supervisor will become resource constraints because it's kind of there is a workload on these supervisors, especially if the problem is very complex or if the number of the sub-agents is increasing. And there is kind of limited flexibility, especially, as we said, if the complexity of the sub-agents increase or the number of the sub-agents increase. I would like to talk about something related to the memory here, but I think let's keep it for the next slides. Another architecture is the so it's the l'architecture hiérarchique, in which we have a supervisor always, and instead of sub agents, we have sub teams. So the supervisor is going to be a supervisor of sub teams. It will add more flexibility. It will add more specialization for the entire system. So, for example, here we have a programming team supervisor, we have a design team supervisor, and each sub supervisor, if you want, um is going to work with his own team, and then all the results are going to be delegated or sent to the big supervisor or the first supervisor. Here, for the pros, there is a scalability. Instead of having kind of a bread first search, right? In the previous one, here we have kind of I forgot the word. We go. I mean, the tree is going tabut. Okay. Another point is effective error handling. So the failure recovery at that type of architecture is very interesting. So you can localize the error in the right level. For example, if there is an error in the programming team, you can still work with the other team, the design team, without any problem. At the time, in the meanwhile, you will figure out the other problem. About the cons, first of all, we have the coordination overhead. Coordination is always an issue if you don't work on it. So you need to have it in mind that I need to coordinate, I need to work on my infrastructure. I need to have a clear design strategy for what's going inside. Another one is the state sync, which is a bit challenging when we have kind of many levels. So you need to pay attention to the synchronization of your states all over the levels. Now, what is the use case or the main use case here? Generally, if we are working on something that is complex, on kind of large scale simulation or complex enterprise automation or something that is very big. So it would be, I mean, scalable. It would be interesting to use that kind of architecture. Now, there is another thing that we call network agent architecture. So in this case, we have kind of many agents, and they can all communicate between them. So there is no leader. Here, for example, if sometimes we put a leader here, sometimes we have a leader, and the other agents, instead of communicating only with the leader, they can communicate between them. So they can collaborate. Yes. So mainly this type of architecture, we use it when we need kind of a decentralized collaboration, or when we need when the agents need to, for example, exchange intermediate outputs or adapt, etc. So I mean, it depends on the case. It depends on the situation. So you need to be aware about your problem statement, about what do you need, and you choose the right one for you. Now, maybe I need to add another word here, or it's fine. The last one is sequential expertise for deep problem solving. This is what we call workflows. So generally, you will find the workflow name for that type of architecture. It means there is a sequential a sequential list of agents. The first agent will send the output to the second one, and the second one to the third one, etc. It's similar to what one agent does, but here we are making sure that our agents are going in depth. For example, here the research agent has access to his tools, and there is a kind of well-detailed prompts, and it can run for for kind of a good time, and then the outputs will be sent to the second agents. Here, just between brackets, one of the best practices is to standardize your outputs. So try to create kind of models when you work with agents. Try to create models for the outputs of your agents so that you help them to give always the best, or not the best output, but a structured output. So the next agent is always receiving the same structure of the output, etc. That will help the whole system to run effectively. So one of about the pros of that type of architecture. First of all, we have the deep specialization, as I said, and each agent will excel in at its specific task without task with optimized logic. Yes, the logic is going to be optimized for the agent itself. For the cons, we have the sequential latency. So in this type of architecture, the running is going to be sequential, so we will not be able to parallelize. And there is the state transfer. About the state transfer, to overcome this problem, as I told you, you need to use the static model output for each agent, so you can have a good state transfer. Now we will try to organize our minds when we talk about implementation with a simple guide. So the steps here, I will try to give you some steps to help you to organize your work. So the first step is to define your use case and architecture. So you need to ask some questions. What is the complexity of your task? And this will give you an idea about going to multi-agents or not. Do you need kind of parallel processing? If you need that, it means try to create kind of a parallel architecture instead of, for example, going to the workflows. What level of specialization is required? And here you will get as an output your the definition of your sub-agents. How important is fault tolerance? The fault tolerance and checking the failures inside your system is very interesting. So try to have a protocol for that. The next step is to choose your framework. There is a lot of frameworks today: LangGraph, CrewAI, AutoGen, LangChain, Agno, and it depends on your use case. So sometimes, for example, they say that CrewAI is good for to handle multi-agent systems. AutoGen, for example, for research and development. LangGraph, if you want to have, let's say, if you want to have the hand on the low level. Agno is amazing for agentic systems. I have been using it since 1 year till now, and there is a big development. They are really working to maintain the framework. For example, one of the problems that we talked about them, the communication or the setting of the infrastructure. For example, if you choose one type of the architecture, It's always a problem if you don't work on your infrastructure. And with Agno, they have kind of a very good infrastructure, so you can build on top of it your multi-agent system, and at the same time you have access. It means if you want to change something about the protocols of communication, about anything, you have access to this as well, because it's an open source framework. So the choice of framework is very interesting and will play a pivotal role in your let's say development experience. Third, the third step is to design the agent roles and responsibilities. So as we said, you need to define your agents with their roles and the responsibilities, their boundaries. Uh, Try to put a single responsibility for each agent. Put a clear boundaries of your agents. The communication protocols are as well interesting, and they are kind of you will have them automatically when you choose the architecture. You will get the communication protocols, except maybe the communication with the database. You need to decide about this. For example, do you give a whole or do you give the ability to any agent to have access to the whole context, or only the lead agents, the team leader? Or for example, the visibility over the memory as well. Do you give the visibility to all of the agents, the leader and the sub agents, or only the leader? It means there is a lot of things to take into consideration and to decide about. Same for the error handling. So plan your failure scenarios. It's really interesting. The next step is to implement the communication patterns. That case, if you are working from scratch, it means you are starting without any framework, or if your framework doesn't handle the type of communication that you are using, or if you want to use something that doesn't exist in your framework. So you need to have kind of an infrastructure setup. And if you are using one of the frameworks that handles everything, then it's fine. You can go directly to the next step. And the next step is add memory and context management. Now, for the memory, to be honest, it was one of the big, let's say, the hardest tasks for me at the beginning when I started to work with agentic systems, because it's really, I mean, you at the beginning, when you think about it, it seems like it's something easy, but when you go in depth, you will find that um, there is some confusions, there is some things that you need to implement, to decide about. So every let's say each engineer is defining its own or his own architecture of the memory. This architecture is one of the architecture I used in one of the projects in our company. So we used a multi-layer memory. The first one is the short-term memory. Of course, let me put you in the context. Let's say that you have a multi-agent system or an agent that is running, and of course I am a user and I'm running this agent in a session, of course. So I need to have kind of a memory inside the same session. It means when I use the agent for the nth time, it should remember the n-1 time, right? So here where we put it the short-term memory, that maintains the context of the current session, and it tracks the active conversations, just like ChatGPT. You see, for example, if you go to your previous chats, you have always the context maintained. And we try to organize the sessions per user. So, for example, one user that has many sessions, it has access always, the user has access always to the sessions, and the knowledge that is coming from those sessions is stored, so that if I go to if I create a new chat in the next time, it has always that knowledge about me. And by the end of each session, I try to summarize everything and send it to the long-term memory of the user, just to keep that context. And then for the long-term memory, so it stores kind of knowledge about the user information, insights, preferences, etc. And it's kind of recognizes the recurring patterns and recalls past interactions, so that we can personalize the responses based on the accumulated experiences. So kind of it's boring if you start if you start from scratch in each chat. So it's really interesting to have kind of uh, uh, a knowledge base, let's say. And we used a knowledge base. That knowledge base was mainly kind of a document DB or database, where we store some domain knowledge, for example, the brand voice, some structured references, etc. And we try to put it as a vectorial database, so that if we need information from that knowledge base, we use kind of agentic RAG to get that information and don't read the whole database, because you need to pay attention to that detail. If you are bringing something from the memory, it means you are adding it into your context, and this context so this context is going to be sent to the LLM, and the LLM context window is limited. And each time you have a conversation, so your context window is going to be increased. And at certain time, you will reach the maximum of the context window, and your system will just stop. So it would be interesting to think about mechanism to optimize that context window. For example, here in our case, we could, for example, use the whole document DB. We add the whole document DB to the context, but this is not optimal. If I need only one information from the document DB, then I need just to bring that information. And this concept of knowledge in Agno, it's very, I mean, the idea came from there. So they try to present that type of memory, if you want, and it's very interesting. I mean, if you think about it. The next step is to implement your tool integration. So each agent is going to use a tool, and of course you try to implement them. We have many types of tools. We have the search APIs, or APIs in general, let's say. We have some tools to process data. We have, for example, tools to use external services, mainly through APIs, or lately through MCP, or you create and code your own tool. The last step is testing and optimizing, or optimization. Testing and optimization. Testing is really interesting. You need to have kind of a culture of testing, and especially the unit tests. You try to test your, for example, if you implemented a function, try to create a unit test for the function. If you implemented a sub-agent, try to test that agent like by itself, and then try to do some integration testing, the agent with its own environment. And then the next step is to implement the end-to-end system, so the complete workflow. This is what we call complete workflow validation. If it's working well, the chain of tool usage, the chain of agents call, etc. And of course, to have kind of visibility over all the, the steps, you need to implement an observation strategy. We will talk about it later. And there is also another thing, which is the performance testing, which means the latency, the metrics, the number of tokens that you used, the cost uh, of run, etc. Now there is some things or some let's say considerations that we need to take when we talk about production ready systems. First of all, there is the coordination complexity. The challenge here is that you need to manage the interaction between multiple agents, and at the same time you need to keep it like under control, because if you add, as we said, for example, for the second architecture, which is the coordinator architecture, if you add a lot of agents, then the complexity is going to explode, and you need to pay attention to that. So some of the solutions that we can propose: implement clear communication protocols. You see, like I talked a lot about the communication protocols, so pay attention, please, to that. Use supervisor patterns for large systems, and if the system goes very large, very into a very large complexity, then go maybe more into the hierarchical architecture. You can have more control and over, all the levels and all the sub teams. It would be interesting as well to establish a task queue and a scheduling system, and monitor agents' interactions through logins. Logins are really interesting, and that if you are using or you are a fan of observation, then observation will help you. Today we have a lot of platforms that provides observation solutions. So I will present one of them in the next slides. The other point is context consistency. The challenge here is to maintain consistent understanding across all the agents as they share information. So I think the challenge is clear. So the solutions that we propose is, first of all, try to implement a shared memory system. Memory is really interesting. Pay attention to it. Try to use message passing with a structured format. What do we mean by this? Is that the output of the agent should be formatted, if you want, with a clear format or a model, what we call a model, so that that the agents always receive the same structure of the information and produce the same structure of information. Try to regular the context synchronization and version control for shared state is really interesting. We are running out of time, so I need to be a bit fast for the next slides. We arrive to the debugging and observation, and this is something that I really like. So the challenge that we talk about here is that when the systems goes or scale and start to be complex, we want always to have kind of a clear visibility and understand what's happening across multiple agents. So the best way is to use the observability platforms, or to create your own observability strategy using the loggings. Now, for example, here, one of our systems that we are working with, when you run your system in production, you have always the observability about what is going there. For example, here this was one of the manipulation. this is the start, and then we invoke the marketing team agents, and then here we need to the team agent is using OpenAI chat, and then it's gonna use the delegate task to member tool, and it's going to delegate this task to the ideation agent, and I'm going to have the answer. The ideation agent is going to use the OpenAI chat, and then use the web search, and then etc. You see, so you have kind of um, an idea about the steps or the chain of tool usage, and the chain of, yes, let's say, tool usage. Now, for LangFuse, I'm just giving you an idea about the interface. You have a lot of things to discover there. I really encourage you to check it, and it's open source and free to use. So here for the tracing, for example, for that special task, we have the user ID, we have the session ID. They give you some metrics here. For example, the latency, the total cost, and which environment you are using. For example, we tried, if you have a development and production environment, it will be specified here, and an idea about the graph of execution, and you have visibility or a preview about the inputs and the outputs of each step here, with log view and the scores, etc. You can check as well the information per sessions, per users. So it's really interesting, the observability side. You can as well use the prompt management functions here. It means you can have kind of prompt versioning. You try the first prompt, at the second prompt, at the third prompt, and you change between the prompts, and you test the performance of your system. Cool. The last, is it the last point? Yes, I guess it's the last point. Cost and resource management. When you start working in and paying for resources, so you will be really interested by the cost. So you need to use kind of, or to think about the models to use, which APIs to choose. Try to optimize the token usage. For example, the trick that I told you about in with the memory, when we use the knowledge base, it's interesting as well. You can select a model per task. For example, if the task is complex, you can use, for example, GPT-4. If it's simple, then you can use 4.0 or 3.5. If it depends on the task. Since you are having a multi-agent system, so each agent can use its own model. There is no problem in that point, and that's one of the benefits of multi-agent systems. Now, there is a case study that I would like to share with you. I don't know if we will have time to finish it or not, but we'll try to do it like in fast way. So it was shared by Anthropic. It's a multi-agent research, their multi-agent research system. So it's a concrete system. This case, it kind of illustrates how multi-agents collaborate, or multi-agent collaboration can dramatically improve the reasoning depth. At the beginning, Anthropic, they had one agent for research. For example, if you research for an information, or they do a research function, and then they try to create a multi-agent system just for that functionality of research, and the performance went, increased in a crazy way. So the problem is that yes, this was this illustration, I took it from their official website. You can find the article and read it by your ease. So the traditional agents, they or the traditional single agent models underperform in open-ended research tasks generally. So in that situation where the reasoning path isn't predefined, for instance, when investigating a topic, or the process is dynamic, or each kind of discovery change when you search for the next. So single agents generally process these tasks sequentially, which makes them path dependent, and you can't kind of paralyze them. And the context is always limited, as we said, when we have sequential running. In other words, so those models weren't very performant. So on Tropic, they tried to design an architecture that could think in parallel. So they have lead agents, and they created some sub agents. So this lead agent will try to create a plan of search and delegate the tasks to those sub agents. And then, of course, as we said, the sub agent will always send the answer to the next or to the lead agents. This was a more detailed process diagram about the mechanism. I need just to ask the organizers if I can have 5 minutes more just to explain this, or we skip. Hello, are you here? Let me check. Yeah, all right, thank you, hello. So we will have an extra 5 minutes. So in this system, the lead agent will receive the complex research task, and then, as we said, it decomposes the query. The sub-agents will independently, as you see, search for the information. For example, one will search in the browser, another one will search in the documents that they have, another one will search, for example, in social media, etc. And each sub-agent returns the condensed summary to the lead. And then the lead will synthesize everything, and you can see that we are saving into the memory, of course, the context, and when we need it, we retrieve it. So for some key interactions here, or key design choices for the communication, they used message passing, or what we call prompt chaining, between the lead and the sub-agents. For the memory, each agent has a local context window. This is what I was talking about. Their decision here was that each agent has its own local context window, just to make sure that the context window is not going to explode for the whole system. And the lead agent maintains the global memory, so the sub-agent doesn't have access to the global memory. For coordination, the coordination was iterative. There were a feedback-driven delegation, and the lead agents can reassign, for example, a task, or refine a subtask, etc. So it has this ability. For the impact was very interesting. And after sharing this article from Anthropic, many people start thinking about truly about the multi-agent system, because at the beginning it was just a research idea. So the performance gain was very interesting. We had a gain by plus 90.2% performance improvement. The efficiency was high because the sub-agents were running in a parallel execution, and there were kind of a breadth first mastery. This is interesting when you have kind of, as we said, a coordinator architecture. Now, even if we had a good improvement, there were some challenges. First of all, the token costs. The token cost was, I mean, it's exploded. So you need to always put into consideration that when we use multi-agent systems, the token cost is going to be very high. That's why you need to optimize, and here comes the good engineer compared to the bad engineer, if we can say this. There is economic trade-offs, so you must always pay attention about, as we said, the cost compared to the added value, and there is some coordination limits. They discovered that, for example, if you go for kind of complicated tasks, the coordination is going to be limited, and the efficiency is going to be quite less compared to simple tasks, let's say. So we remember the quote is that multi-agent systems are used when the value justifies the cost of extra complexity. And always we need to keep in mind that as engineers, you need to be responsible about your design choices, and you need to think about how to optimize the cost, either the economical cost or the token cost or the latency or all the those parameters. To conclude, some key takeaways that we will finish with. First of all, multi-agent systems excel where single agent struggles. So in complex tasks, in specialized expertises, and fault tolerance. Choose your frameworks carefully based on your technical requirements, the requirements of your project, and the complexity of the project. Start simple and gradually increase and sophisticate your system. At the beginning, if you start big, it depends. There is two schools. There is people who start big and they have sophisticated architecture. There's people who start small and try to keep always in mind the big goal, and always plan for the next steps. I'm more fan of the second school. Focus on coordination, on communication. The infrastructure is very interesting. Plan for challenges, as I said, the cost management, the error handling. Observability is your friend through the whole process of development. The last advice is think long term about scalability, maintainability, and evolution of your system. Thank you very much for your time. Yes, we got 3 minutes. We over. Dépassé de 3 minutes. Je suis désolée pour l'équipe organisatrice. If you have questions or if we can have questions, I don't know if we have time or not.
You received one question. It is, did you mean depth first search for the hierarchical agent architecture?
Yes, exactly. That's the one that I missed. Thank you.
Thank you so much, our dear speaker Ilham Bika, for this insightful talk. The knowledge you shared is highly appreciated. Thank you so much again. And
Yeah,
now, for our dear community, don't go anywhere. We will see you in our second talk in few seconds. Thank you so much.
you're welcome.
Have a good evening. Thank you so much, Ilham, for this session. It was amazing. We appreciate it a lot. Sorry, your mic is closed. I can't hear you.
Right. avec plaisir. J'espère ما كثرتش الهضرة بزاف.
No, not at all. It was so insightful. والله.
Thank you. Bon courage à vous. You are, I missed to say something. GDG for once, GDG forever. We are always grateful to GDG. Bon courage. ربي يوفقكم إن شاء الله.
Thank you.
Nice to meet you, هلا.
Nice to meet you.
بزاف.
Thank you.
السلام عليكم.
Salam.